Out there, in the cold, silent depths of our solar system, far beyond the orbit of Neptune, hides a world that defies explanation, a tiny, distant enigma named Eris. Discovered in 2005, this dwarf planet shattered our understanding of the cosmos, forcing astronomers to rethink the very definition of a planet. But Eris is more than just Pluto's mysterious twin. It's a puzzle wrapped in ice, a celestial oddity that whispers secrets we've only begun to unravel. What makes this frozen world so peculiar? Why does it challenge everything we thought we knew about the outer reaches of our solar system? And what hidden truths lie buried beneath its icy surface, waiting to be uncovered? Imagine a place where the sun is nothing more than a faint, distant star, where temperatures plunge so low that gases freeze solid, and where a single year lasts over 550 Earth years. This is the realm of Eris, a world so small yet so massive that it threw the astronomical community into chaos upon its discovery. It's not just another rock drifting through space, it's a gravitational heavyweight denser than Pluto, with a surface brighter than freshly fallen snow. Scientists still can't fully explain why. Some speculate it's coated in a layer of reflective methane ice, while others wonder if something far stranger is at work. One thing's for certain, Eris doesn't play by the rules. Tonight, we're diving deep into the 25 most baffling mysteries surrounding this distant dwarf planet. From its bizarre orbit that tilts wildly out of alignment with the rest of the solar system to the unexplained flashes of light occasionally detected on its surface, Eris refuses to give up its secrets easily. Could there be active geological processes happening in this frozen wasteland? Is it possible that Eris holds clues to the formation of our solar system, or even the existence of undiscovered worlds lurking in the shadows? Strap in, because we're about to embark on a journey to the edge of the known, where every answer only leads to more questions. The mysteries of Eris are waiting, and they're more astonishing than you could ever imagine. Eris doesn't just drift through space, it cuts a path so strange that astronomers still struggle to explain it. While most objects in the Kuiper Belt follow relatively flat, circular orbits around the Sun, Eris moves like a cosmic rebel, tracing an elongated, tilted path that veers wildly out of alignment with nearly everything else in our solar system. Its orbit is so extreme that at its farthest point, it's nearly twice as distant as Pluto, only to swing back in at a sharp 44-degree angle. This isn't just unusual, it's a glaring exception to the rules that govern nearly every other object in that icy belt of debris. So what could have thrown Eris so dramatically off course? One leading theory points to Neptune's gravitational pull. In the early days of the solar system, the giant planets may have reshuffled the orbits of smaller bodies like cosmic billiard balls, sending some spiraling outward while dragging others closer. But here's the twist: Eris's orbit is too tilted, even for that explanation to fully account for it. Some scientists speculate that a rogue gravitational nudge, perhaps from a long-lost sibling planet or a close encounter with another massive object, could have sent Eris spinning into its current path. Others wonder if it wasn't born in the Kuiper Belt at all, but was captured from another star system entirely, making it a cosmic hitchhiker with a backstory we've yet to uncover. The mystery deepens when you consider Eris's tiny moon, Dysnomia. Most moons orbit their planets in tidy, predictable patterns, but Dysnomia wobbles unevenly around Eris, as if still feeling the gravitational echoes of some ancient chaos. Could this be a clue to a violent collision that knocked Eris into its odd trajectory? Or is Dysnomia's strange dance evidence of unseen forces still at work in the outer solar system? The unsettling truth is, we simply don't know. Every time astronomers think they've pinned down Eris's secrets, another question emerges, leaving us to wonder, what other surprises is this distant, defiant world hiding? If you were standing on the surface of Eris, you'd need to shield your eyes. not from sunlight, which barely reaches this frozen outpost, but from the blinding glare of the ground itself. This dwarf planet is one of the shiniest objects in our solar system, reflecting almost all the faint sunlight that touches it. Its surface is brighter than freshly fallen snow on Earth, a fact that has left scientists scratching their heads for nearly 2 decades. Most distant icy worlds, like Pluto or Makemake, darken over time as cosmic radiation and interstellar dust stain their surfaces. But Eris gleams like a cosmic mirror, defying every expectation. So what's keeping it so pristine? One leading theory points to methane, frozen so solid it forms a glittering frost. On other dwarf planets, methane ice usually darkens as radiation breaks it down into complex organic compounds, a process we've observed on Pluto's reddish patches. But Eris's extreme distance might be its secret. Out where temperatures hover near absolute zero, methane could be freezing into an ultra-stable form, creating a self-renewing layer that resists discoloration. Imagine a winter landscape where the snow never gets dirty. It just keeps replenishing itself in a slow, otherworldly cycle. Yet methane alone might not explain everything. Some researchers suggest Eris's surface could be coated in something even more exotic. Nitrogen glaciers like those on Pluto, but purer and more reflective. Others speculate that tiny shifts in Eris's orbit periodically heat its surface just enough to vaporize dark spots, leaving behind fresh ice. There's even a fringe hypothesis that geysers or cryovolcanoes might be at work, spewing bright material onto the surface in rare eruptions. The real puzzle isn't just why Eris is so bright. It's why it's unlike anything else out there. Every time we think we've cracked the code, new observations throw us back to square one. Could this be a clue to some unknown process shaping the outer solar system? Or is Eris a frozen time capsule, preserving conditions that vanished everywhere else billions of years ago? One thing's certain, this distant world's glow is more than just a curiosity. It's a beacon shining clues about mysteries we're only beginning to grasp. One of the most baffling things about Eris is what's not there, an atmosphere. Despite being nearly the same size as Pluto, which clings to a thin but detectable envelope of nitrogen and methane, Eris shows no signs of any gaseous veil whatsoever. This is downright strange. If two icy worlds are so similar in size and composition, why does one have even a wisp of atmosphere while the other appears completely bare? The answer might lie in their wildly different orbits. Pluto's path brings it slightly closer to the Sun during part of its long year, allowing just enough warmth to vaporize some surface ices into a temporary, tenuous atmosphere. But Eris, it never gets that close, stuck in the deep freeze of the outer solar system, where temperatures rarely climb above -400 degrees Fahrenheit. Any gases that might escape its surface would instantly freeze solid, collapsing back onto the ground like cosmic frost. It's as if Eris is trapped in permanent winter, too cold even for an atmosphere to form. But there's another possibility, one far more dramatic. Some scientists suspect Eris did have an atmosphere once, only to lose it in a slow-motion disaster. Solar wind, the relentless stream of charged particles from the Sun, could have stripped away gases molecule by molecule over billions of years. Without a magnetic field for protection, something Pluto lacks as well. Eris's air may have simply bled into space, leaving behind the frozen husk we see today. Here's where things get even weirder. Observations suggest Eris's surface contains methane, a gas that should escape easily into space if given the chance. So why hasn't it all vanished? One theory proposes that Eris's extreme cold acts like a cosmic deep freeze, locking methane and other volatiles into an unbreakable icy grip. Another idea suggests occasional bursts of geothermal activity might replenish trace amounts, creating fleeting pockets of gas that vanish before we can detect them. The real puzzle is whether Eris's airless state is permanent, or just part of a cycle we're not seeing. Could shifts in its orbit eventually warm it enough to sprout a temporary atmosphere like Pluto? Or has solar wind left it forever barren? For now, this tiny world keeps its secrets locked in ice, a silent sentinel at the edge of the known. Peering at Eris through telescopes, scientists expected to find a clear chemical fingerprint, something straightforward, like Pluto's mix of nitrogen, methane, and carbon monoxide. Instead, they got a cosmic riddle. The spectral data tells two conflicting stories. Some observations scream methane with its telltale infrared signatures. Others hint at nitrogen dominating the surface, while a few bizarre readings suggest compounds we can't even identify yet. How can one tiny world serve up such contradictory clues? Part of the confusion comes from Eris's extreme distance. Even our most powerful instruments struggle to capture detailed spectra from over 9 billion miles away. The light that reaches us is faint, stretched, and easily contaminated by interstellar dust. It's like trying to identify a spice rack through a fogged-up window while standing a mile away. But distance alone doesn't explain the wild disagreements. Pluto, just as far, gave up its secrets more willingly. Eris seems to be hiding something in plain sight. The methane camp points to the dwarf planet's blinding reflectivity. Pure methane ice, when freshly frozen, can be extraordinarily bright, much like Eris appears. But here's the snag. Methane should darken over time as radiation cooks it into reddish organic gunk, something we've seen on Pluto's darker patches. So why hasn't Eris aged the same way? Some researchers think its methane might be locked in an unusual crystalline form, reshuffling itself under extreme cold to stay pristine. Others propose occasional landslides or cryovolcanic activity could be exposing fresh ice, like a self-cleaning oven on a geological timescale. Then there's the nitrogen argument. On Pluto, nitrogen frost creates vast, glowing plains. If Eris has similar deposits, its reflectivity would make sense. But nitrogen is slippery. It needs just a whisper of warmth to vaporize, and Eris's orbit keeps it locked in a perpetual deep freeze. Could it really stay stable there? A handful of astronomers suggest a compromise. Maybe Eris has methane-nitrogen blends with ratios unlike anything we've seen elsewhere. These exotic ices could behave in ways our current models don't predict. The plot thickens with whispers of even stranger substances. A few studies have detected spectral lines that don't match any known ices. Could Eris harbor minerals forged in conditions unique to the outer solar system? Or might its surface chemistry be altered by interactions with cosmic rays in ways we don't yet understand? Every new observation seems to add another layer to the puzzle, leaving scientists to wonder, is Eris's composition a fluke or a signpost pointing to processes we've never witnessed before? Until a probe makes the long journey to this frozen enigma, we're left piecing together fragments. Each theory fits part of the data but clashes with another. It's as if Eris is deliberately toying with us, revealing just enough to keep us guessing. One thing's clear, this isn't just another icy rock. It's a chemical rebel rewriting the rules of what dwarf planets can be. Eris's lone moon, Dysnomia, shouldn't exist as it does. At least not according to everything we thought we knew about how moons behave. Most moons in the solar system, whether orbiting planets or dwarf planets, follow elliptical paths, their orbits stretched and tilted by gravitational tugs over time. But Dysnomia defies the norm with a nearly perfect circular orbit, clinging to Eris so tightly it's as if the two are locked in a gravitational embrace no force has dared disrupt. This isn't just unusual, it's practically unheard of for an object so far out in the Kuiper Belt. So how did this cosmic oddity come to be? One leading theory suggests a violent past, a cataclysmic collision between Eris and another large icy body, similar to the impact that likely gave Earth its moon. The debris from such a smash-up could have coalesced into Dysnomia, settling into a close, stable orbit over billions of years. But there's a problem. If Dysnomia formed this way, why hasn't its orbit been perturbed by passing objects or the subtle gravitational nudges of other Kuiper Belt residents? The outer solar system is a chaotic place, yet Dysnomia's path remains eerily undisturbed, like a record skipping on the same perfect note. Another possibility is even more intriguing. Dysnomia might not be a native of Eris's system at all. Some astronomers argue its orbit is too pristine to result from a collision, proposing instead that Eris captured this moon as it wandered the Kuiper Belt alone. Capture scenarios are rare but not impossible. Neptune's moon Triton is thought to be a captured object. Yet for Eris, with its puny gravity compared to a giant planet, snagging a moon like Dysnomia would have required a freakishly precise alignment of speed and trajectory. It's the celestial equivalent of threading a needle while blindfolded on a roller coaster. The real head-scratcher is Dysnomia's composition. Observations hint it's far darker than Eris, almost as if it's coated in some sooty material that absorbs light instead of reflecting it. If Dysnomia were born from the same collision that shaped Eris, why wouldn't it share its parents' dazzling brightness? This disconnect has led to wilder speculations. Maybe Dysnomia is a rogue fragment of some long-vanished object, or its surface has been chemically altered by eons of cosmic radiation in ways we don't yet understand. Adding to the confusion, Dysnomia's orbit doesn't just challenge our ideas about moon formation, it throws a wrench into models of how dwarf planets evolve. Most binary systems in the Kuiper Belt, like Pluto and Charon, show signs of gravitational dancing, their orbits gradually shifting over time. Dysnomia, by contrast, seems frozen in place as if time stopped for it alone. Could Eris's intense cold be preserving some ancient equilibrium, or is there an unseen force, a hidden mass, a gravitational anomaly, keeping this moon locked in its perfect loop? Every new observation deepens the puzzle. Dysnomia's existence hints at either a wildly improbable past or a gap in our understanding of celestial mechanics so vast we've yet to even map its edges. It's a reminder that even in our own cosmic backyard, the universe still holds cards it hasn't shown us, and until we send a probe to Eris's distant domain, Dysnomia will keep orbiting in silence, a cryptic moon guarding secrets we can only guess at. Eris isn't just a frozen ball of ice drifting through the outer solar system, it's a cosmic contradiction. When scientists calculated its density, expecting numbers similar to other icy dwarf planets like Pluto or Makemake, the results left them stunned. Eris is far denser than it should be, packing more mass into its compact frame than any known object of its size and composition. This isn't a minor discrepancy, it's a full-blown mystery that forces us to reconsider what might be lurking beneath that gleaming surface. The most straightforward explanation points to a hidden rocky core. If Eris formed with a significant chunk of silicate rock beneath its icy shell, that could account for the extra density. But here's the catch. Most Kuiper Belt objects are thought to be relatively uniform mixtures of ice and rock, leftovers from the solar system's early days when lighter materials were flung outward by the giant planets. For Eris to have such a pronounced rocky core, it would mean either a freakish accident of formation like a collision that stripped away much of its ice, or a previously unknown process that concentrated heavy elements in certain parts of the outer solar system. Yet there's another, even more tantalizing possibility: internal heating. On Earth, radioactive decay in our planet's core keeps things toasty, driving plate tectonics and volcanic activity. Could something similar be happening inside Eris? Even at its frigid distance from the Sun, the decay of radioactive isotopes like uranium or thorium might generate enough warmth to slowly separate heavier materials from lighter ones, allowing rock to sink toward the center over billions of years. It's a slow-motion alchemy, turning a homogeneous ice-rock mix into a layered world with a dense heart. The plot thickens when you consider Eris's reflective surface. If internal heating were at work, you'd expect signs of resurfacing cracks, geysers, or cryovolcanoes replenishing the bright ice. But so far, no such features have been detected. Then again, at this distance, our telescopes might simply be missing subtle clues. Alternatively, Eris's heat could be just enough to alter its density without breaking through to the surface, like a simmering pot with a tightly sealed lid. What makes this puzzle even harder to solve is the contradictory data. Some measurements suggest Eris's density is closer to Pluto's, while others insist it's significantly higher. Part of the problem is pinning down its exact size. Eris's distance and brightness make it notoriously tricky to observe, and even tiny errors in estimating its diameter can throw density calculations into chaos. Without a dedicated mission to visit this distant world, we're left weighing ambiguous clues, trying to decide whether we're looking at a dwarf planet with a secret rocky heart, or something even stranger. One radical theory suggests Eris might not be a native of the Kuiper Belt at all. If it formed closer to the Sun, where heavier materials were more abundant, before being hurled outward by gravitational chaos, that could explain its unusual composition. It's a long shot, but in the outer solar system, where every rule seems to have an exception, even the wildest ideas can't be ruled out. For now, Eris guards its secrets tightly. Is it a frozen world with a hidden core of rock defying the icy norms of the Kuiper Belt? Or does some unseen process unique to this distant realm sculpt dwarf planets in ways we've yet to imagine? Every answer we think we have only leads to deeper questions, leaving us to wonder what other surprises this tiny, enigmatic world might hold. Eris isn't just cold, it's unnaturally, inexplicably cold, even for the outer solar system. Models predict that a world this size at this distance should settle into a certain temperature range based on sunlight absorption and internal heat. But when astronomers measured Eris's surface, the readings plunged lower than anyone anticipated. We're talking about temperatures dipping close to -400 degrees Fahrenheit, colder than Pluto despite their similar compositions. This isn't just a quirk, it's a violation of expectations that hints at something fundamentally different happening on or inside this tiny world. So why does Eris defy the thermal rules? One possibility lies in its dazzling brightness. Most icy bodies absorb a fraction of sunlight, converting it into trace amounts of warmth. But Eris's mirror-like surface reflects almost all light that hits it, like a cosmic disco ball bouncing rays back into space. Without absorbing solar energy, it can't generate even the meager heat seen on other Kuiper Belt objects. It's the difference between wearing a black shirt on a sunny day versus a polished silver one. You'll stay cooler in the reflective material, no matter how faint the sunlight. But reflection alone doesn't fully explain the anomaly. Some researchers suspect Eris's internal structure plays a role. If the dwarf planet lacks radioactive elements or has a unique geological makeup that traps heat at its core, little to no warmth would seep upward to the surface. Imagine a thermos bottle in space designed to keep icy contents frozen against all odds. Alternatively, Eris's orbit might be key. Its elongated path takes it farther from the Sun than Pluto ever ventures, subjecting it to prolonged deep freeze periods where any residual heat has eternity to dissipate. The wildest theories involve exotic ices or atmospheric ghosts. Certain methane-nitrogen mixtures, when frozen under extreme pressure, can conduct heat bizarrely, essentially creating a natural refrigeration effect. If Eris's crust contains these materials, it might actively repel warmth rather than just passively staying cold. There's also the tantalizing, if speculative, idea that trace amounts of sublimating gases could create a cold trap, similar to how evaporating sweat cools your skin. Even a vanishingly thin haze of nitrogen vaporizing from the surface might carry away critical amounts of energy, leaving the ground chillier than models account for. Every explanation raises new questions. If exotic ices are at work, why don't we see similar cooling on other Kuiper Belt objects? If internal heat is absent, how does Eris maintain geological features that suggest occasional resurfacing? The deeper we dig, the clearer it becomes. Eris isn't just breaking the rules, it's rewriting them, forcing us to reconsider how heat behaves in the solar system's most remote corners. Until we land a probe on its gleaming surface, this temperature puzzle will remain one of its most stubborn secrets, a frosty enigma at the edge of the known. If Pluto is the solar system's moody artist shifting colors, growing and losing its atmosphere with the seasons, Eris is its stoic, unchanging counterpart. Despite having an axial tilt even more extreme than Earth's, which should create dramatic seasonal shifts, this distant dwarf planet shows no visible fluctuations as it crawls through its 550-year orbit. No darkening, no brightening, no detectable transformation at all. It's as if time stands still on this frozen world, and that defiance of expectations has astronomers scrambling for explanations. The most obvious culprit is sheer distance. Pluto's seasons, though subtle, are driven by its elliptical orbit, bringing it periodically closer to the Sun, allowing faint sunlight to vaporize some surface ices. Eris, by contrast, never gets that reprieve, stuck in the Kuiper Belt's deep freeze where temperatures hover near absolute zero. Even its summer would barely register. The Sun's warmth here is less a ray of heat and more a whisper lost in the void. Any seasonal changes might simply be too minuscule for our telescopes to catch, like trying to detect a snowflake melting in a blizzard. But distance alone doesn't fully explain the mystery. Eris's extreme axial tilt, a staggering 78 degrees compared to Earth's 23, should create wild oscillations in sunlight distribution, with one pole baking in perpetual daylight for centuries while the other sinks into endless night. Yet no such variations appear in the data. One theory suggests its surface ice is so thick and inert that even these drastic shifts can't crack its frozen equilibrium. Imagine a glacier so massive that turning a blowtorch on it for a few minutes leaves no mark. Eris's ice might behave similarly, absorbing or reflecting sunlight with no lasting effect. Then there's the enigma of atmospheric buffering, or lack thereof. Pluto's thin nitrogen atmosphere acts like a seasonal moderator, redistributing warmth and frost across its surface. Eris, with no detectable atmosphere, has no such mediator. Any changes would have to come from direct solar influence, and at this distance, that influence is practically non-existent. It's possible Eris experiences seasons in ways we can't yet measure: microscopic sublimation of frost, or slow migrations of volatile gases trapped just beneath the surface. But without an orbiting probe, these processes remain speculative at best. The wild card, Eris's reflectivity, might be masking its own secrets. That mirror-like surface could be recycling sunlight so efficiently that any localized warming from seasonal shifts gets instantly diffused, leaving no detectable signature. Or perhaps the dwarf planet's geology is suppressing changes altogether. If cryovolcanism or other internal processes are replenishing surface ice at a steady rate, they could be resetting any seasonal markers before they have time to develop. The unsettling truth is that we're still peering at Eris through a keyhole, limited by technology and distance. Future telescopes, like the upcoming 30-meter telescope, might finally spot the faint seasonal whispers we've missed. Until then, this icy world remains a paradox, a planet with all the ingredients for dramatic change, yet frozen in cosmic stillness, challenging us to rethink what seasons even mean at the edge of the solar system. Among the many puzzles Eris presents, few are as visually striking as the so-called bright spots, mysterious patches of intense reflectivity scattered across its surface like cosmic beacons. These aren't just subtle variations in brightness, they're glaring anomalies, some gleaming up to 50% more vividly than the surrounding terrain. On a world already notorious for its mirror-like sheen, These concentrated flashes of light stand out like searchlights in a snowstorm, defying every expectation of how icy surfaces should behave in the outer solar system. The leading explanation points to cryovolcanism, a process where underground liquids or slushy ices erupt onto the surface, depositing fresh, unblemished material. On moons like Europa or Enceladus, such eruptions leave clear geological signatures, fissures, domes, or vast smooth plains, but Eris complicates the story. No visible cryovolcanic features, no cracks, no ridges have been detected alongside these bright patches. If eruptions are happening, they must be vanishingly subtle, perhaps oozing out in slow, gelid flows that freeze before they can form noticeable structures. Alternatively, the eruptions could be rare, occurring only once every few millennia, leaving each bright spot as a lingering scar from some ancient upheaval we happen to catch at the right moment. Another theory suggests these spots might not be volcanic at all, but the aftermath of impacts. When a meteorite strikes an icy surface, it can blast away older, radiation-darkened material, exposing pristine ice beneath. The problem: most impact craters in the Kuiper Belt darken over time as cosmic rays bake their floors into tar like residue. Eris's bright spots show no signs of such decay, maintaining their brilliance despite enduring the same harsh environment as their neighbors. Some researchers propose a twist. Maybe the impacting bodies were rich in volatiles like methane or nitrogen, which refroze after the collision into a glassy, highly reflective glaze. It's the difference between kicking up dust and spilling a vat of liquid mirror. Then there's the wild-card possibility: electrical phenomena. On Earth, charged particles from the solar wind interact with our atmosphere to create auroras. Could something similar be happening on Eris's surface, but frozen in place? Laboratory experiments show that irradiating methane ice with high-energy particles can create thin, crystalline layers that sparkle with unnatural brightness. If Eris's weak gravity allows solar wind to directly bombard certain areas, these electrofrost deposits might accumulate over eons, creating permanent bright zones where physics takes an unusual turn. The most perplexing aspect isn't just the spots' existence, it's their persistence. On active worlds like Europa, fresh ice quickly dulls under radiation. Eris's patches, by contrast, seem locked in stasis, neither fading nor spreading. This could hint at a self-renewing cycle, where subsurface forces continually feed material to the surface, or at a type of ice chemistry so stable it resists the relentless weathering of space. Either way, these gleaming anomalies serve as a reminder. At the solar system's edge, even the simplest observations can unravel into profound mysteries, waiting for some future explorer to decode their frozen secrets. Eris spins at a pace that defies the rhythm of the solar system. While most dwarf planets and Kuiper Belt objects whirl through their days in a matter of hours, Pluto completes a full rotation every 6.5 Earth days. Eris drags its rotation out to a sluggish 25.9 hours. That's slower than Mercury, slower than Mars, slower than even Earth's moon. In a realm where celestial bodies typically pirouette with abandon, Eris moves like it's stuck in cosmic molasses. What could be putting the brakes on this distant world? The prime suspect is Dysnomia, Eris's enigmatic moon. Gravitational tugs between a planet and its satellite can dramatically alter rotation speeds over time, a process known as tidal locking. Our own moon has done this to Earth, subtly slowing our planet's spin by microseconds each year. Dysnomia, despite its small size, orbits unusually close to Eris, creating a gravitational tug-of-war that could be sapping its parent's rotational energy. Given enough time, billions of years, this dance might even force Eris to present only one face to its moon permanently, just as the moon always shows Earth its near side. Yet there's a wrinkle in this theory. Tidal locking usually requires liquid oceans or malleable interiors to dissipate rotational energy effectively. Europa's subsurface ocean, for example, helps Jupiter's gravity slow its spin. but Eris is presumed to be frozen solid with no sloshing layers to absorb Dysnomia's pull. Unless, of course, it isn't as rigid as we think. Some models suggest radioactive elements or residual heat from Eris's formation might keep a sliver of its interior just pliable enough for tidal forces to take hold. It's a long shot, but in the outer solar system, long shots have a habit of proving true. Impact trauma offers another compelling explanation. A colossal collision early in Eris's history, perhaps the same one that spawned Dysnomia, could have robbed the dwarf planet of its original spin, leaving it in this slowed state. Computer simulations show that glancing blows between icy bodies can transfer angular momentum in chaotic ways, sometimes leaving one object rotating far slower than before. If Eris suffered such a hit, the evidence might be buried beneath its icy crust, fractures, density variations, or even a displaced core. The real puzzle isn't just why Eris spins slowly, it's why other similarly sized Kuiper Belt objects don't. Makemake and Haumea, both smaller than Eris, whirl much faster, completing rotations in under 4 and 4 hours respectively. This inconsistency hints that Eris's lethargy isn't just about size or distance. Something unique, whether Dysnomia's influence, a catastrophic impact, or an internal structure we haven't imagined, must be at play. Perhaps the answer lies in a combination of factors. A primordial collision could have both birthed Dysnomia and sapped Eris's spin, with the moon's gravity then fine-tuning the rotation over eons. Or maybe Eris's extreme axial tilt plays a role, interacting with solar tides in ways we haven't modeled. Every explanation raises new questions, leaving us to wonder, is Eris's slow spin a quirk of its violent past, or a clue to processes we've yet to discover in the frozen reaches of the solar system? One thing's certain, in a universe that favors motion, this dwarf planet's leisurely pace stands out like a deliberate whisper in a room full of shouts. When gazing at images of Eris, one detail immediately jumps out: it's suspiciously smooth. Unlike most ancient worlds in the outer solar system, which bear the scars of countless asteroid impacts, Eris's surface looks almost polished, as if someone took a cosmic buffer to its icy plains. This absence of craters isn't just odd, it's a glaring contradiction. At over 4.5 billion years old, Eris should resemble a pockmarked relic, a frozen archive of violent collisions. So where are the scars? The most plausible answer lies beneath the surface, literally. Scientists suspect Eris might be geologically active, with sluggish rivers of nitrogen or methane ice oozing upward over millennia, filling in craters like slow-motion spackle. On Pluto, similar processes create vast, unblemished plains like Sputnik Planitia, where convecting ice effectively erases ancient wounds. But Eris presents a puzzle. It's smaller and colder than Pluto, with far less internal heat to fuel such activity. For ice to flow here, something extraordinary must be at work, perhaps residual warmth from radioactive decay, or tidal flexing from Dysnomia's gravitational pull, kneading Eris's interior like cosmic Play-Doh. Yet there's another, more radical possibility. Eris's extreme reflectivity could be masking its craters entirely. Fresh ice sheets, especially those rich in methane, might form transparent layers that optically fill depressions, creating the illusion of smoothness from afar. Imagine pouring liquid glass over a pothole. From a distance, the road looks flawless. If Eris's surface ices sublimate and recondense in a continuous cycle, this self-healing effect could perpetually hide its battle scars. The implications are staggering. If Eris is actively resurfacing itself, it challenges everything we thought we knew about dwarf planets in the Kuiper Belt. These worlds weren't supposed to be dynamic, just frozen fossils of the early solar system. But Eris whispers a different story, that even in the coldest, darkest reaches of space, geological life might persist, quietly reshaping landscapes over eons. Every smooth patch on its surface isn't just a missing crater. It's a clue that the outer solar system is far more alive than we ever imagined. when astronomers point their infrared telescopes at Eris, expecting the familiar fingerprint of methane or nitrogen ice, what comes back is anything but straightforward. The data paints a conflicted picture. Some wavelengths align perfectly with expectations, while others spike or dip in ways that make no sense for a simple icy world. It's like tuning a radio to a known station, only to catch fragments of alien static bleeding through. These infrared anomalies aren't just minor quirks, they're glaring inconsistencies that challenge our basic understanding of what Eris is made of. One of the biggest headaches comes from a band of absorption features around 3 micrometers, a range where methane ice should dominate. Instead, the readings show a jagged, uneven pattern, as if something is either masking the methane or mixing with it to create a spectral hall of mirrors. Some researchers point to contamination from complex organic molecules, the kind that form when radiation cooks simple ices over eons. But here's the catch: Eris's surface is supposed to be too cold and pristine for that level of chemical evolution. Other dwarf planets like Pluto show these darkened compounds clearly, yet Eris's bright sheen suggests its ices haven't undergone the same transformation. So why the infrared chaos? Instrument limitations might be partly to blame. Observing an object 9 billion miles away pushes our technology to its limits, and Earth's own atmosphere can distort infrared signals like heat haze on a desert highway. Yet, even after accounting for these factors, the discrepancies persist. A tantalizing possibility is that Eris harbors minerals never before seen in the Kuiper Belt. Salts, silicates, or even exotic forms of water ice forged under pressures impossible to replicate on Earth. These materials could be bending the infrared light in ways our current models don't anticipate. Imagine trying to identify a spice by smell alone, only to discover it's a blend of ingredients you've never encountered. The plot thickens when you consider Eris's temperature. Infrared spectra are heat-dependent, and Eris's unnatural chill could be warping the readings in unexpected ways. Certain ices, when cooled to near absolute zero, exhibit quantum behaviors that alter how they absorb light, a phenomenon normally studied in labs, not on distant worlds. If Eris's surface is a natural quantum icebox, it might be generating spectral signatures that defy textbook explanations. Perhaps the boldest theory suggests we're seeing the ghost of an ancient atmosphere. Frozen gases trapped in Eris's ice like bubbles in amber could create layered spectral distortions as sunlight penetrates to different depths. On Pluto, seasonal changes stir up its thin atmosphere, leaving faint infrared traces. Eris, with no active air to speak of, might instead preserve atmospheric remnants in its ice, a frozen archive of lost gases that occasionally taint the data. Until we send a probe to sample Eris's surface directly, these infrared riddles will linger. Each new observation adds another piece to the puzzle, but the full picture remains frustratingly out of focus. What's clear is this: Eris isn't just reflecting light. It's reflecting our own ignorance, showing us how much we still have to learn about the frozen fringes of our solar system. When Eris was first discovered, it sent shockwaves through the astronomical community, not just for its existence, but for the brazen claim that this tiny world might actually be larger than Pluto. The initial measurements, based on brightness and assumed reflectivity, suggested Eris could be up to 27% more massive than its famous cousin. This was the final straw that forced the International Astronomical Union to reconsider what truly defined a planet, ultimately leading to Pluto's controversial demotion. But here's the twist: later observations revealed Eris might not be bigger after all. In fact, it could be slightly smaller. The uncertainty around its true size isn't just a technical hiccup, it's a window into how much we still don't understand about the outer solar system. The heart of the problem lies in how we measure distant objects like Eris. Without sending a probe to fly by, astronomers rely on indirect methods, primarily observing how much sunlight the dwarf planet reflects and how its gravity tugs on its moon Dysnomia. Eris's extreme brightness through the first curveball initially interpreted as evidence of a larger surface area, hence a bigger diameter. But what if that reflectivity wasn't due to size, but something far stranger? Later studies, including stellar occultations where Eris passed in front of distant stars, suggested a diameter closer to 2,326 kilometers, just a hair under Pluto's 2,377. The margin is so slim that even today the debate isn't fully settled. This rivalry isn't just academic pedantry. The size question ties directly into Eris's density, composition, and even its origin story. If Eris is smaller but more massive than Pluto, as some data suggests, it implies a rockier core, something that shouldn't exist so far out in the icy Kuiper Belt. Alternatively, if they're nearly the same size, why does Eris's surface behave so differently, resisting darkening and seasonal changes? The uncertainty fuels a deeper mystery. Are we looking at two variations of the same type of world, or is Eris something entirely unique, masquerading as Pluto's twin? The controversy also highlights the limitations of our tools. Measuring objects billions of miles away is like trying to gauge the width of a coin from across a football field using only a flickering flashlight. Tiny errors in brightness assumptions, Dysnomia's orbital calculations, or even the shape of Eris itself slightly squashed at the poles due to rotation can tilt the scales. New telescopes like the upcoming Vera C. Rubin Observatory promise sharper answers, but for now, Eris lingers in that tantalizing gap between almost Pluto's size and just a bit smaller. What makes this debate so compelling isn't the numbers themselves, it's what they represent. Eris isn't just challenging Pluto's status, it's forcing us to confront how little we know about the frozen fringes of our cosmic neighborhood. Every new measurement, every refined estimate carries the potential to rewrite our understanding of these distant worlds. And until we finally send a mission to Eris, this dwarf planet will keep dancing just out of reach, its true size remaining one of the solar system's most stubborn enigmas. Eris's silence isn't just auditory, it's magnetic. While Pluto may harbor a faint magnetic field, hinted at by subtle interactions with solar wind, Eris broadcasts nothing but radio silence. This absence of detectable magnetism isn't just a curiosity, it's a glaring clue about what's happening or not happening deep within this frozen world's core. The contrast with Pluto is stark. Though neither dwarf planet boasts a strong magnetic shield like Earth's, Pluto's tenuous atmosphere and surface features suggest some internal dynamism, perhaps a slushy, conductive layer beneath its icy crust generating weak magnetic ripples. Eris, by comparison, shows no such signs. If it has a magnetic field at all, it's so feeble that even our most sensitive instruments can't catch a whisper. This raises a pivotal question. Is Eris's core fundamentally different, or are we simply not listening closely enough? One possibility cuts to the heart of planetary science. Eris might be geologically dead. Without a molten or electrically conductive layer, there's nothing to generate a dynamo effect, the churning of conductive material that creates magnetic fields in planets like Earth. Pluto's potential field could stem from residual heat keeping its interior partially fluid, but Eris's extreme distance and higher density might have allowed its core to freeze solid eons ago, shutting down any magnetic activity like a cosmic power switch. Yet there's an alternative explanation, one that hints at technological limitations rather than cosmic ones. Detecting magnetic fields at such distances is like trying to hear a pin drop in a hurricane. Solar wind interference, instrument noise, and the sheer faintness of any potential signal could be masking Eris's magnetism entirely. Even Earth-based observations of Pluto's field remain contentious. For Eris, 9 billion miles away, the challenge is exponentially greater. Future missions equipped with magnetometers might finally crack the case, but for now, the data is frustratingly mute. The wild card in this puzzle, Eris's density. While its high mass-to-size ratio suggests a rocky core, rocks alone don't guarantee magnetism. They need to be moving, melting, or chemically interacting. If Eris's core is rich in non-conductive silicates or locked in a rigid, crystalline state, even residual heat wouldn't spark a dynamo. Compare this to Jupiter's moon Ganymede, where a liquid iron core and tidal heating conspire to create the solar system's only moon-born magnetic field. Eris lacks both ingredients, leaving it adrift in magnetic solitude. The implications ripple beyond one dwarf planet. If Eris truly lacks a field, it could redefine how we categorize icy worlds. Magnetic activity often signals internal heat, geological vitality, even the potential for subsurface oceans. Eris's silence might place it in a new class altogether, frozen to the core, a relic of the solar system's coldest, most inert depths. Or just maybe it's hiding a secret we haven't yet learned to hear. Until we press our ears or probes closer, this magnetic mystery will linger, a quiet enigma in the endless dark. Eris didn't just stumble into its name, it earned it. In Greek mythology, Eris was the goddess of strife and discord, a troublemaker who famously tossed the golden apple inscribed "to the fairest" into a wedding party, sparking the feud that led to the Trojan War. When astronomers chose this moniker for the dwarf planet in 2006, they knew exactly what they were doing. Eris's discovery didn't just add another world to our solar system. It shattered the fragile consensus on what a planet even was, igniting a bitter debate that still simmers today. The irony is almost poetic. A celestial body named for chaos became the catalyst for scientific upheaval, forcing the International Astronomical Union to draw lines in the cosmic sand. But the naming process itself was far from straightforward. Before settling on Eris, the Discovery team considered other mythological figures, including Persephone and Leela, names evoking beauty and playfulness. Yet as the planet definition controversy raged, the team leaned into the drama, opting for a title that mirrored the turmoil they'd unwittingly unleashed. Eris's moon, Dysnomia, named after the goddess's daughter and the spirit of lawlessness, sealed the joke with a wink. It was a rare moment of scientific gallows humor, acknowledging the chaos while immortalizing it in the official records of the cosmos. The name's cultural ripple effects were immediate. Almost overnight, Eris became shorthand for disruption, popping up in think pieces about scientific revolutions and even inspiring tech startups to brand themselves as Eris-like disruptors. Meanwhile, Pluto loyalists, those still stung by its demotion, embraced the dwarf planet's mythological reputation, painting Eris as the villain in Pluto's downfall. Memes sprouted across the internet, Eris as a cosmic homewrecker, a sly trickster, even a celestial Thonos snapping Pluto's planetary status out of existence. Yet the deeper irony lies in Eris's true nature. Unlike its namesake goddess, the dwarf planet is anything but chaotic. It's a world of eerie stillness, frozen in time, its surface unblemished by the very upheaval its discovery caused. The name is a misdirection, a cosmic inside joke that distracts from the real mystery. Why such a quiet, enigmatic world became the flashpoint for one of astronomy's fiercest modern debates. Perhaps that's the final twist. In mythology, Eris sowed discord with a single apple. In reality, all this dwarf planet had to do was exist. Eris doesn't orbit alone. It drifts through one of the solar system's most enigmatic regions, a cosmic badlands known as the scattered disk. This vast, sparsely populated belt of icy objects lies beyond Neptune, stretching into the void with orbits so stretched and tilted they seem flung there by some ancient celestial catastrophe. While most Kuiper Belt objects cluster in relatively flat, orderly paths, scattered disk members like Eris careen through space like rogue comets, their trajectories wild and unpredictable. What makes Eris's position so peculiar isn't just its distance, it's the isolation. Unlike Pluto, which dances among swarms of similar-sized neighbors, Eris reigns almost alone in its patch of darkness, a frozen sovereign with no obvious court. The scattered disk wasn't always this sparse. Billions of years ago, during the solar system's chaotic youth, Neptune's migrating gravity hurled countless icy bodies outward, scattering them like billiard balls. Most were ejected entirely, becoming interstellar nomads. A handful, like Eris, found unstable orbits at the edge of the abyss. But here's the puzzle. Eris's orbit is too extreme, even for this unruly crowd. Its path tilts nearly 45 degrees off the solar system's plane, farther than almost any other known object in the scattered disk. This isn't just a gentle nudge from Neptune, it suggests a far more violent past. Some researchers speculate Eris might have been slingshotted by a close encounter with an unseen sibling planet, one later ejected from the solar system entirely. Others wonder if it was jostled not just by Neptune, but by a passing star during the Sun's birth cluster, a fleeting gravitational handshake that left Eris permanently adrift. The real mystery isn't how Eris got there, it's why it stayed. Most scattered disk objects eventually succumb to gravitational tugs, either drifting into the Oort cloud or plunging inward as comets. Yet Eris persists, its orbit eerily stable despite the chaos surrounding it. This stability hints at a delicate balance, as if Eris found a gravitational sweet spot where Neptune's influence cancels out the galaxy's tidal forces. It's like a marble rolling around the rim of a bowl, poised perfectly between falling in and flying off. Adding to the intrigue are Eris's missing neighbors. Computer simulations suggest the scattered disk should contain dozens of Eris-sized worlds, yet we've found barely a handful. Is Eris the lone survivor of some primordial massacre, its siblings ejected or shattered long ago? Or are we simply blind to an unseen population, their faint light lost in the glare of the Milky Way? Every telescope survey deepens the question, turning Eris's isolation from a curiosity into a cosmic whodunit. Perhaps the most tantalizing clue lies in Eris's kinship with Sedna, another scattered disk recluse with an even more extreme orbit. Both worlds might be relics of a lost population, ice dwarfs exiled from the inner Kuiper Belt by Neptune's migratory tantrums. Or they could be stolen goods captured from another star during the Sun's infancy, now stranded in our system's farthest reaches. The answer, if we ever find it, could rewrite the story of our solar system's birth. For now, Eris spins in silence, a frozen castaway guarding secrets older than the planets themselves. Eris didn't just redefine our solar system, it tore up the rulebook entirely. When this icy world was discovered in 2005, it wasn't merely a new member of the planetary club. It was a wrecking ball crashing into astronomy's most sacred classification. At the time, textbooks confidently listed 9 planets, with Pluto holding its place as the faint, frozen oddball at the edge. Then Eris arrived, shining brighter and appearing potentially larger than Pluto, forcing astronomers to confront an uncomfortable truth. If Pluto was a planet, so was Eris. And if both were planets, how many more lurked in the Kuiper Belt waiting to be found? The crisis was immediate. Suddenly, the tidy planetary lineup we'd all memorized was on the verge of exploding into dozens, even hundreds of new worlds. The International Astronomical Union faced a dilemma: expand the definition of a planet to include Eris and its kin, or draw a hard line. In 2006, they chose the latter, introducing 3 strict criteria. A planet must orbit the Sun, be round from its own gravity, and have cleared its orbit of other debris. Pluto and Eris, both sharing their orbits with icy neighbors in the Kuiper Belt, failed the final test. Overnight, Pluto was demoted to dwarf planet, and Eris became the celestial poster child for a controversial new category. But the decision was far from unanimous. Anger erupted at the IU's General Assembly, with some scientists storming out in protest. To this day, factions within the astronomical community argue the rules were arbitrary, even unscientific. The heart of the dissent lies in the cleared orbit clause. Critics point out that even Earth, Mars, and Jupiter share their orbital zones with asteroids technically failing the IU's own standard. Others argue that geology, not location, should define a planet. If a world is massive enough to pull itself into a sphere, it's earned the title. Under this logic, Eris, with its complex surface and potential internal activity, checks every box. Planetary scientist Alan Stern, leader of NASA's New Horizons mission to Pluto, famously dubbed the IU's decision sloppy science, insisting that Eris and Pluto deserve full planetary status based on their intrinsic properties rather than their celestial zip codes. What makes this debate more than academic is the growing list of Eris-like worlds. Since 2006, we've discovered Makemake, Haumea, and Gonggong, all icy, round, and orbiting in the Kuiper Belt. If Eris is a planet, so are they. The IU's definition, intended to bring clarity, has instead sparked a quiet rebellion. Some museums and textbooks still list Pluto as the 9th planet, while others grudgingly accept the dwarf planet label. Public sentiment, too, remains fiercely pro-Pluto, with schoolchildren and scientists alike refusing to let go of the 9-planet model they grew up with. The deeper question isn't just about labels, it's about how we classify nature's complexity. Eris, by its mere existence, exposed the flaws in our human-made categories. Is Ceres, the round asteroid, less of a planet than Mercury simply because it shares its orbit? Does Jupiter, with its entourage of Trojan asteroids, truly meet the IU's standard? The debate rages because Eris forced us to confront an uncomfortable truth. The universe doesn't care about our tidy definitions. It creates worlds on a spectrum from pebbles to gas giants, and our attempts to box them into binaries will always be imperfect. Perhaps the final irony is that Eris, named for the goddess of discord, became the catalyst for this cosmic identity crisis not by being unusual, but by being utterly ordinary. It's a typical Kuiper Belt object, one of hundreds, maybe thousands, just like it. The real disruption wasn't Eris's discovery, but our realization that the solar system is far richer, stranger, and more resistant to categorization than we ever imagined. And that's a revolution no IU vote can undo. Eris's surface doesn't just gleam, it flickers. Astronomers have long been puzzled by the dwarf planet's overall reflectivity, but closer inspection reveals something even stranger: patches of wildly inconsistent brightness scattered across its frozen terrain. Some regions shine with the brilliance of fresh snow, while others appear noticeably duller. Not enough to resemble Pluto's dark stains, but enough to defy the idea of a uniform, pristine ice sheet. These albedo variations aren't random noise. They're a coded message about what's happening beneath the surface, and so far, every attempt to decode them has left scientists with more questions than answers. One explanation points to cryovolcanic resurfacing. If pockets of warmer ice lie beneath Eris's crust, occasional eruptions could spew fresh, bright material onto specific areas while leaving others untouched. The challenge, unlike Pluto's Sputnik Planitia, a vast, smooth plain clearly shaped by geological activity, Eris shows no obvious volcanic features, no fissures, no domes, no telltale ridges. If cryovolcanism is at work here, it's happening in a way we've never seen before. Stealthy, almost ghostly, with eruptions so subtle they leave no trace beyond these shimmering stains. Then there's the impact theory. Meteor strikes could expose brighter subsurface layers, but here's the catch: Eris's surface lacks the expected craters to match these bright spots. Unlike Saturn's moon Enceladus, where impacts trigger brilliant plume eruptions, Eris's potential impact zones don't follow the usual patterns. Some bright patches cluster in ways that suggest fractures or faults, hinting at tectonic activity, yet the dwarf planet's small size and frigid temperatures make such forces hard to explain. How could a world this cold and distant still crack and shift like a living planet? The most tantalizing possibility involves Eris's chemistry. Different ices reflect light in wildly different ways. Methane frost, for example, glows far brighter than nitrogen or carbon monoxide frosts. If Eris's subsurface is a layered cocktail of these materials, uneven sublimation, where some ices vaporize faster than others, could create patchwork reflections. Sunlight might be slowly sculpting the surface, exposing methane-rich deposits in some areas while leaving nitrogen-dominated zones to darken slightly. It's a delicate dance between temperature, composition, and time, one that could explain why Eris's brightness variations don't align with any single geological process. Yet even this explanation falls short when faced with the data. Spectroscopic readings show no clear correlation between albedo and ice type, leaving researchers to wonder if something else entirely is at play. Could solar wind, those relentless charged particles streaming from the sun, be selectively darkening certain regions? Or might Eris harbor unseen, reactive minerals that interact with its ices to create localized brightening effects? The more we study these variations, the clearer it becomes. Eris isn't just a static ice ball. It's a world of hidden dynamics where even the faintest gleam might hold the key to understanding what lies beneath. What makes these albedo mysteries so compelling isn't just their defiance of models. It's what they imply about the outer solar system as a whole. If Eris, a tiny world at the edge of nothingness, can sustain such complexity, what other surprises lurk in the darkness? Every flicker of light from its surface is a reminder that even the coldest, most distant reaches of our cosmic neighborhood are far from dead. They're whispering, shifting, hiding secrets in plain sight, if only we know how to listen. Pluto boasts a miniature solar system, 5 known moons flitting around it, from tiny Styx to the massive Charon. Yet Eris, its near twin in size and composition, stands alone with just Dysnomia, a solitary moon barely a tenth its size. This cosmic imbalance isn't just odd, it's a glaring anomaly that challenges our understanding of how dwarf planets capture and retain satellites. If Pluto's chaotic gravitational dance can host an entourage, why does Eris's system feel so eerily empty? The most compelling clue lies in Dysnomia's peculiar dominance. Unlike Pluto's moons, which orbit in a relatively flat plane, Dysnomia circles Eris in a tight, circular path, exerting a gravitational influence far beyond its modest size. Computer simulations suggest such an arrangement could act like a celestial vacuum cleaner, clearing stray debris from Eris's vicinity over billions of years. Any smaller moons that might have formed alongside Dysnomia or wandered too close could have been either flung into the void or swallowed by their larger sibling. It's a brutal game of gravitational king of the hill, with Dysnomia as the undisputed champion. But there's another twist: Eris's extreme distance. The Kuiper Belt's outer reaches are sparsely populated compared to Pluto's neighborhood, meaning less raw material for moon formation. While Pluto likely accumulated its satellites from the debris of ancient collisions in a crowded orbital zone, Eris may have faced a lonelier birth. Fewer collisions mean fewer chances to spawn moons, leaving Dysnomia as the sole survivor of a quieter cosmic nursery. Yet some researchers argue the absence of small moons might be an illusion. Eris's brightness coupled with Dysnomia's faintness could be masking smaller companions. Pluto's tiniest moons were only discovered after painstaking searches by the Hubble Space Telescope. Eris, 10 times farther away, could easily hide moonlets in its glare. Even New Horizons struggled to spot Pluto's smaller satellites until it was nearly on top of them. Without a dedicated flyby mission, Eris's potential retinue of minor moons might remain invisible, lurking just beyond our detection. The wild card in this mystery, Dysnomia's dark surface. Most small moons in the Kuiper Belt reflect light brightly, making them easier to spot against the blackness of space. But Dysnomia's sooty complexion absorbs light like cosmic charcoal, raising the possibility that Eris's system harbors other dim, elusive companions camouflaged in the darkness. If these hypothetical moons share Dysnomia's composition, our current telescopes would struggle to find them, like searching for black marbles in a shadowy room. The deeper implication isn't just about missing moons, it's about the violence hidden in Eris's past. Pluto's multi-moon system suggests a relatively orderly formation history, while Eris's solitude hints at something more turbulent. A cataclysmic collision powerful enough to birth Dysnomia might have been too violent to leave other survivors, scattering potential siblings into the void. Or perhaps Eris's wild orbital tilt exposed it to gravitational tides that stripped away smaller moons over eons, leaving Dysnomia as the last witness to a lost lunar family. Until we send a probe to Eris's frozen domain, this lunar loneliness will remain one of its most persistent puzzles. Is Dysnomia truly the lone sentinel of a quiet system, or just the visible tip of a hidden lunar iceberg? The answer could rewrite not just Eris's history, but our understanding of how dwarf planets grow and lose their celestial companions. Eris shouldn't defy time, yet it does. Conventional wisdom says every object in our solar system formed from the same primordial disk of gas and dust roughly 4.5 billion years ago. But when scientists attempt to date Eris using standard techniques, analyzing crater counts, surface composition, and orbital dynamics, something doesn't add up. Some estimates suggest this frozen world might be significantly younger than its peers, a cosmic impossibility that's forced astronomers to consider radical alternatives. Could Eris be an interstellar hitchhiker captured from another star system entirely, or are we simply misreading the clues from our distant, frozen enigma? The age paradox begins with Eris's suspiciously smooth surface. In the outer solar system, crater density acts like a cosmic clock. The more impacts, the older the world. Pluto and its moon Charon bear the pockmarked scars of eons of collisions, matching their expected age. Eris, by contrast, appears relatively unblemished, as if it hasn't endured the same bombardment. One explanation is geological activity erasing craters, but that raises another problem. Eris lacks the internal heat source needed to drive such resurfacing. Unless, of course, it hasn't existed long enough to accumulate scars in the first place. Then there's the orbital evidence. Most Kuiper Belt objects, including Pluto, settled into their current orbits during the solar system's chaotic infancy, shaped by Neptune's gravitational nudges. Eris's extreme tilt and elongated path don't fit this narrative. Computer simulations struggle to reproduce its trajectory using standard models of planetary migration, leading some researchers to speculate it arrived much later, perhaps flung into our system during a close encounter with another star. The math is contentious but not implausible. During the Sun's early years, it dwelled in a dense stellar nursery, where gravitational tugs between neighboring stars could have swapped icy worlds like cosmic trading cards. The most tantalizing clue comes from Eris's composition. Spectroscopic studies reveal subtle chemical differences between its ices and those of native Kuiper Belt objects. Certain isotopic ratios, think of them as atomic fingerprints, don't quite match the rest of our solar system's outer debris. These anomalies could hint at an exotic origin, forged in the protoplanetary disk of another star before being stolen away. It's not without precedent. The interstellar visitor Oumuamua proved objects wander between star systems. Eris, in this scenario, would simply be a permanent immigrant rather than a passing tourist. Yet there's a simpler, if less thrilling, possibility. Dating distant objects is fraught with uncertainty. Without direct samples, scientists rely on proxies like reflectivity and cratering rates, metrics that can be skewed by factors we don't yet understand. Eris's extreme brightness might mask craters, making its surface appear artificially young. Its peculiar orbit could result from rare but natural gravitational interactions, not an extraterrestrial origin. Even the chemical differences might stem from unique preservation conditions in the scattered disk, where cold and isolation keep ices pristine in ways we've never observed elsewhere. The debate cuts to the heart of planetary science. How well do we really know our cosmic neighborhood? If Eris is an outsider, it implies our solar system's history is far more dynamic and violent than we imagine. If it's a native sun, then our models of planetary formation are missing crucial pieces. Either way, this icy enigma forces us to confront an uncomfortable truth. The farther we peer into the darkness, the more we realize how much we've yet to learn. Eris keeps half its face eternally hidden from Earth's prying eyes, a cosmic sleight of hand that's persisted since its discovery. Unlike planets that rotate briskly enough to reveal their full surfaces over time, Eris's sluggish spin and extreme distance ensure we've only ever glimpsed one hemisphere in detail. The other side remains a blank canvas, a dark-side enigma that could harbor anything from towering ice mountains to vast, uncratered plains. This isn't just a gap in our knowledge, it's a glaring blind spot that forces us to question everything we think we know about this dwarf planet. Observing Eris's far side isn't just difficult, it's nearly impossible with current technology. At an average distance of 9 billion miles, even the Hubble Space Telescope can only resolve Eris as a tiny, shimmering dot. The dwarf planet's rotation is so slow one day lasts almost 26 Earth hours that capturing multiple hemispheres would require years of continuous observation. Compounding the challenge, Dysnomia's orbit blocks certain angles, casting shadows or obscuring views like a celestial photobomber. The result, we've mapped Pluto's entire surface down to glacial flows and nitrogen dunes, while half of Eris remains as mysterious as the far side of the Moon was before the space age. What makes this blindness so tantalizing are the potential disparities between the two hemispheres. On Pluto, the differences are dramatic. The heart-shaped Sputnik Planitia dominates one side, while the other is riddled with jagged ice blades and chaotic terrain. If Eris follows suit, its hidden face could Chinese letter our assumptions. Some models suggest an ancient impact might have tilted Eris's axis, leaving one pole in perpetual shadow where exotic ices like nitrogen or carbon monoxide could accumulate unseen. Others speculate tectonic forces driven by residual heat or tidal flexing from Dysnomia might have sculpted one hemisphere into fractured ridges or cryovolcanic domes we've yet to imagine. The wild card is Eris's reflectivity. If the far side lacks the bright methane frost coating its visible half, it could mean entirely different geological processes at work. Perhaps solar wind, striking one face more directly, has darkened it over eons. Or maybe Dysnomia's gravitational pull has triggered asymmetrical resurfacing, with one side continually renewed by ice geysers while the other stagnates. Without direct observation, these theories remain frozen in speculation. The stakes are higher than mere curiosity. On Enceladus, unseen fractures on the Moon's far side were found to be spewing life's building blocks into space, a revelation that rewrote our understanding of icy moons. Eris's hidden face could hold similar surprises, crevices leaking ancient volatiles, cryolava flows, or even an impact basin so colossal it reshaped the dwarf planet's interior. Until a probe like New Horizons makes the epic journey to Eris, this cosmic peekaboo game will continue, leaving us to wonder what secrets, and perhaps what new definitions of dwarf planets, lie waiting in the dark. Eris broadcasts nothing but static, a complete absence of the faint radio crackles that whisper from other dwarf planets. While Pluto emits sporadic bursts likely tied to solar wind interactions, and even distant Sedna shows subtle radio signatures, Eris remains stubbornly mute. This radio silence isn't just a technical footnote. It's a glaring anomaly that could rewrite what we know about icy worlds at the solar system's edge. The contrast with Pluto is especially jarring. Despite sharing similar sizes and compositions, Pluto's tenuous atmosphere interacts with charged particles to create weak but detectable radio waves, a phenomenon observed during New Horizons flyby. Eris, by comparison, doesn't even hum. One explanation points to its bone-chilling cold. At temperatures nearing absolute zero, electrons in Eris's surface ices might lack the energy to generate detectable emissions. It's like comparing a live wire to one frozen solid. Without movement, there's no signal. Yet temperature alone doesn't solve the puzzle. Haumea, another frigid dwarf planet, emits faint radio pulses believed to stem from crystalline water ice in its interior. Eris's silence suggests something fundamentally different is happening beneath its crust. Perhaps its core lacks the conductive materials like salt-rich oceans or metallic compounds that enable other worlds to sing. Alternatively, Eris's magnetic field, if it exists at all, could be too weak to channel charged particles into detectable patterns. The wild card is dysnomia. Moons often generate radio noise through tidal friction, as seen with Jupiter's volcanic Io. But Dysnomia's orbit is too circular and stable to produce the gravitational stretching needed for such activity. This leaves astronomers with a haunting possibility. Eris might be geologically dead, its interior frozen into utter stillness. No molten layers, no shifting tides, just a silent, frozen vault holding secrets we can't eavesdrop on. Or the answer could be simpler. Radio emissions from the Kuiper Belt are notoriously faint, often drowned out by cosmic background noise. Our telescopes might not yet be sensitive enough to catch Eris's whispers. Future missions equipped with advanced radio spectrometers could finally break the silence, revealing whether this dwarf planet is truly mute, or just speaking in a language we've yet to learn. Until then, Eris's quiet remains one of its most profound mysteries, a reminder that some cosmic conversations happen in frequencies beyond our reach. Eris isn't just playing tricks with light, it might be changing colors. Over the past 2 decades, astronomers have reported subtle but persistent shifts in the dwarf planet's hue, flickering between a pale off-white and a faint reddish tint. These aren't dramatic transformations like Mars's rusty palette or Pluto's seasonal darkening, but the variations are just enough to defy easy explanation. Is Eris's surface undergoing some slow-motion chemical metamorphosis? Or are we seeing the limits of our own technology, mistaking cosmic static for a shifting canvas? The case for real color change hinges on chemistry in deep freeze. On other icy worlds, radiation from the sun and cosmic rays can bake surface ices into complex organic compounds, darkening and reddening them over time. Pluto's reddish patches, for example, are thought to be radiation-processed methane. But Eris throws a wrench into this tidy narrative. Its overall brightness suggests its surface should be resisting such discoloration, yet the color shifts persist. Some researchers propose a compromise. Maybe Eris's veneer of methane frost is thin enough in places to allow sporadic radiation effects, creating patchwork stains that come and go as fresh ice sublimates or erupts from below. Imagine a glacier that occasionally bleeds rust only to heal itself with new snowfall. The alternative, that these shifts are observational illusions, is equally compelling. Measuring color at the edge of the solar system is like judging a painting through frosted glass. Earth's atmosphere, telescope calibration errors, and even the sun's variable activity can skew the data. Eris's distance means we're capturing photons that have traveled 9 billion miles. The slightest interference along that journey could tint the results. Even Hubble's keen eye struggles with this challenge, sometimes registering redness that later observations fail to confirm. It's the astronomical equivalent of an old television losing signal, brief flashes of distortion mistaken for content. Yet one dataset refuses to fade into noise. In 2015, a team using the Very Large Telescope in Chile detected a consistent reddish tinge in Eris's southern hemisphere, a hue that vanished when the same region was re-examined in 2022. If real, this could hint at asymmetric surface processes where one pole darkens while the other stays pristine. The leading theory, Eris's extreme axial tilt, might expose its southern latitudes to more solar wind during certain phases of its orbit, cooking the ices there like a rotisserie chicken basted with charged particles. The stakes here are higher than chromatic curiosity. If Eris's color changes are genuine, they imply a world far more dynamic than its frozen exterior suggests, one where chemistry, geology, and maybe even cryovolcanism are quietly at work. If they're illusions, they reveal just how blind we remain at these distances, where even the most advanced telescopes guess at truths hidden in the dark. Either way, this cosmic chameleon keeps us questioning, its palette shifting not just in color but in meaning, reminding us that some mysteries only deepen the longer we stare. Beneath Eris's frozen crust, a tantalizing possibility lurks, one that defies the icy logic of the outer solar system. Could this distant dwarf planet, colder than the void between stars, conceal a hidden ocean? It sounds like science fiction, but the evidence, both for and against, paints a far more intriguing picture than we might expect. Start with the numbers. Eris's unusually high density suggests a rocky core far larger than Pluto's, wrapped in a thick shell of ice. On its own, that doesn't imply liquid water. But combine it with the dwarf planet's radioactive elements, uranium, thorium, and potassium, and the math gets interesting. These elements decay over time, releasing heat. On Earth, that heat fuels volcanoes and tectonic shifts. On Eris, trapped under miles of ice, it might just be enough to maintain a slushy, saline layer between rock and frost. It wouldn't be a roaring sea, more like a sluggish cryobrine oozing through cracks if it exists at all. The counter-argument is the cold. Eris's surface hovers near -400 degrees Fahrenheit, colder than Pluto by a significant margin. At those temperatures, even antifreeze-like compounds like ammonia or salts would struggle to keep water liquid, and yet we've seen this paradox play out elsewhere. Saturn's moon, Enceladus, and Jupiter's Europa both harbor subsurface oceans despite their frozen exteriors, thanks to tidal heating from their massive parent planets. Eris has no such gravitational powerhouse nearby, but Dysnomia's subtle tugs combined with radioactive decay might provide just enough energy to tip the scales. Then there's the chemistry. Spectra of Eris's surface show hints of methane, nitrogen, and maybe even carbon monoxide, all volatile ices that shouldn't stick around for billions of years without replenishment. One explanation, these compounds might be leaking from below, carried upward by slow geological processes or even cryovolcanic vents. If Eris's interior is warm enough to mobilize these ices, why not water? The clincher, or lack thereof, comes from magnetic fields. Oceans with dissolved salts conduct electricity, generating detectable magnetic signals. Europa's ocean, for instance, creates subtle disturbances in Jupiter's magnetic field. Eris, though, shows no such fingerprint, but here's the twist. Without a strong external magnetic field to interact with, even a salty ocean might remain electromagnetically invisible. Our instruments could be staring right through it, none the wiser. The debate rages because the stakes are cosmic. If Eris has an ocean, it joins an elite club of worlds where liquid water persists against all odds, and where the ingredients for life might just exist in the darkness. But if it doesn't, then its density and chemistry become even harder to explain, pointing to geological processes we've yet to discover. For now, this frozen enigma keeps its secrets locked away, leaving us to wonder what might stir beneath the ice, if anything at all. Eris remains one of the last great uncharted frontiers of our solar system, a world brimming with unanswered questions, yet no spacecraft has ever paid it a visit. That could change sooner than we think. NASA and other space agencies have begun sketching ambitious mission concepts to unravel Eris's secrets, each more daring than the last. But reaching this distant dwarf planet won't be easy. The journey alone would take over 25 years with current propulsion technology, requiring a spacecraft to survive the coldest, darkest reaches of space longer than any probe before it. One leading proposal, dubbed the Eris Odyssey, would slingshot past Jupiter for a gravity boost, then cruise silently for decades before finally entering orbit around Eris in the 2050s. Its instruments would map the dwarf planet's hidden hemisphere, measure its gravitational field to confirm or deny the existence of a subsurface ocean, and even drop a lander to taste its exotic ices firsthand. But the challenges are staggering. Solar panels are useless so far from the sun, meaning the mission would rely on nuclear power, a limited and politically sensitive resource. Communication delays would stretch to over 12 hours, forcing the probe to operate with near-total autonomy. And then there's the cost. Estimates range upwards of $3 billion, a tough sell for a single target when missions like New Horizons visited multiple Kuiper Belt objects. Private space ventures have floated wilder ideas. Breakthrough Starshot, the initiative behind interstellar nanocraft, has toyed with adapting its laser sail technology for a high-speed flyby of Eris. A tiny probe propelled by Earth-based lasers could theoretically zip past the dwarf planet at a fraction of the time, but capturing useful data at such velocities would require breakthroughs in miniaturized sensors and imaging. Even if it worked, the flyby would last mere hours, leaving most of Eris's mysteries intact. The scientific payoff, however, could revolutionize planetary science. Cracking Eris's enigmas might reveal overlooked processes shaping all icy worlds, from Pluto to the exoplanets orbiting distant stars. Its bizarre density and reflectivity could rewrite textbooks on planetary formation, proving the outer solar system is far more dynamic than we ever imagined. And if by some chance Eris does harbor a hidden ocean, it would expand the habitable zone of our solar system to unthinkable distances, raising profound questions about where life might thrive. For now, Eris lingers just out of reach, a frozen sphinx guarding its riddles. But with each passing year, technology narrows the gap between dream and reality. The question isn't if we'll explore Eris up close, it's when and how boldly we're willing to reach into the unknown. One day, the answers to its 25 mysteries won't be speculations whispered across 9 billion miles, but data etched into history by the first spacecraft to touch this cosmic outpost. Until then, the future of Eris exploration remains a thrilling cliffhanger, one we're all waiting to see unfold. From its inexplicable reflectivity to its magnetic silence, from the enigma of its missing craters to the whispers of a hidden ocean, Eris stands as a cosmic rebel, an icy outlier that refuses to fit neatly into any box we've built to understand the solar system. Think about it, this tiny world, smaller than our moon, has rewritten textbooks, shattered definitions, and left scientists scratching their heads with every new observation. Why is its surface brighter than freshly fallen snow when it should be darkened by eons of radiation? How does it maintain such a pristine, uncratered facade despite billions of years in the Kuiper Belt's celestial shooting gallery? And what secrets lie beneath that gleaming shell? Exotic ices, a rocky core defying all expectations, or even the faintest glimmer of subsurface liquid? The mysteries don't stop there. Dysnomia's perfectly circular orbit defies the chaotic dance of most moons. Eris's extreme tilt and elongated path suggest a violent past or perhaps an interstellar origin. Its infrared spectra tease compounds we can't yet name, while its radio silence hints at geological stillness or a language of signals we simply can't hear. Even its color seems to shift like a cosmic chameleon, flickering between shades we struggle to explain. 25 puzzles, each more confounding than the last, and every answer we think we have only opens 3 new questions. Here's the thing about Eris, it's not just a collection of scientific curiosities. It's a mirror held up to our own ignorance, reflecting how much we still don't understand about the universe's coldest corners. This dwarf planet doesn't follow the rules not because it's broken them, but because we never knew the true rules in the first place. Every anomaly, every contradiction is a clue waiting to be deciphered, a whisper from the edge of the known that says, "Look harder." Dig deeper. So where do we go from here? The next chapter of Eris's story belongs to missions not yet launched, telescopes not yet built, and maybe even to you, the curious minds watching this video. Will we send a probe to crack its frozen code? Will new technologies reveal the truths hidden in its light, its orbit, its silence? One thing's certain, Eris isn't done surprising us. And if history's taught us anything, it's that the universe's greatest lessons come from the outliers, the exceptions, the cosmic rule breakers. Stay tuned. Stay questioning, because out there in the dark, Eris is still spinning its mysteries, and the next big discovery might be just one observation away. The solar system's greatest puzzle isn't solved yet, and that's what makes it so thrilling.